Okay, so let's have a look at Splunk and machine learning. So overall, we'll look at some of the methods that are applied into machine learning, and then we'll go straight into some Splunk experiments using machine learning. So in the first part of the presentation, we looked at how we could use the fit command to be able to fit a machine learning model onto a data set. So this involved us using input lookup to be able to read in the data set here. And then we define our machine learning model onto this, and we can save this as a new model if we require. Okay, in this case, we're predicting for petal length, and we're using all of the parameters inside the data set, or all of the fields. So if we want, we can change this to the parameters that we wish to train on. And then we can rerun the model again. So this is the prediction here that it made. This is the petal length that we're training for. And then this is a prediction here. So we can rerun that model, and then we'll get some new predictions based on the fields that we're training on. So we just let this one finish, and then we'll go and make a start on that. So, okay, so this is predicted petal length here, and this is the actual values, and this is the predicted values. What we're missing here is the score on whether this is a good model or not. Okay, so the main classifications that we have are outliers or anomalies. We can classify in terms of a category outlier. Those categories are typically string values or something limited within a set. That's anomaly detection, local outlier factor in one class SVM. Then we can have numeric ones where we can take standard deviations or a number of standard deviations, or interquartile or medium absolute deviation. And that gives us our anomalies. And in cybersecurity, we often use anomalies or outliers to be able to define when something moves away from standard. Then we can have our prediction methods, again, category or numeric. With numeric, we often have our regression methods, linear regression, random forest regressor, lasso, and so on. And then for category, we can use logistic regression and SVM. And often we have to prepare our data. So for that, we might want to pre-process our data to normalize it, to bring the values together so that they are similar in scope. We can use the robust scaler or standard scaler here, or we might extract fields from our data, things that are not significant we could dismiss, and fields that are we could include, and that will simplify our machine learning model. And what we can also do is to reduce the number of features down. For that, we can use principal component analysis, or PCA, or TF-IDF, which will reduce the number of features down into a manageable form without losing much. Then often what we do is we cluster, we define a number of clusters, and then we put our data set points into each of the clusters. K-means, dbScan, BERT, and spectral clustering are methods that are used here. And along with this, we might use forecasting to be able to determine something over time, such as the number of logins at 9 o'clock on a Monday morning, to make a prediction, and that's based on daily activity and time of the day, and also the month and the year, and so on. Okay, so it's important that we understand each of the methods and which ones work best. So the first thing we'll look at is to be able to predict our categories. So with Splunk, we basically just open up, we install the machine learning toolkit, and then we can go ahead and actually set up an experiment. In this case, we're going to predict categorical fields here. We set up the name of the experiment and then we'll go ahead and set up the experiment and look at the different methods involved. Okay, so in this case we're going to look at firewall traffic, and we'll filter it down to 50,000 records because there's many more than that. Then inside this data set we'll look at logistic regression first. That's a category, as a categorical prediction, because in this case we have a device which is infected or not, so that's two different categories. Okay, so we've got used by malware or not used by malware. So what we'll do is that we'll select the used by malware to predict, and then we'll use the rest of the data set to be able to predict whether the device has been infected by malware. And of that, we'll use 70% of the data set to train, and we'll keep back 30% and then analyze the success of the model based on the 30% that we have here. Okay, so it's logistic regression used by malware to predict, and then we'll take all the other parameters and then we'll fit a model, and then hopefully what we'll get is that the data set will actually define whether we have a true positive or a false positive. Okay, and from that we can actually define a confusion matrix, which will give us our basic quality there. So in these areas there was no not used by malware, and we predicted no, so we get a percentage there. And here, yes, it's used by malware, and we predicted it correct. Our false positives and incorrect guesses are here and here. We want to minimize those values and maximize these ones to get to 100%. So the way that we do this is with these measurements: precision, recall, accuracy, and F1 give us our basic metrics for success. We want to get these as near to 1.0 as possible. Okay, so let's go and start this experiment up. Okay, so here is our data set here. Okay, and we can have a look to see what that data set looks like: bytes received, bytes sent, destination port, destination IP address, and so on. There's a serial number, and then at the end we've got used by malware. So in this case, this data set has been recorded, and then it's been marked whenever the device in question is being used by malware. So what we need to do is to define a machine learning model which will look at each of these features and then find a good model to predict in the best way possible. Okay, so we'll go ahead, and so we're going to be using logistic regression, and then we'll try the other models in a little minute, but we'll try logistic regression, and then we'll select used by malware here. And then what we do is we go and select each of the other features apart from the one that we're actually training on. Okay, and then we can vary the amount of data that we use to be able to train the model. In this case 70, and then 30% will be left, and the machine will try out the other 30% to see if it was right or wrong. And because we have a big data set, it's quite a lot of records there, the 15,000 or so, which will be used to be able to see if it got them correct or not. Okay, so let's fit our model. So we're using logistic regression, and we'll see obviously the values that we get will vary because it depends what part of the data set that we actually use to be able to train on, so it won't always be the same. So it's just fitting the model just now. and we'll have a look to see what our scores are. Okay, and there we go. So here we go. So we can see here, and this was used by malware, and it's predicted yes. So it got that correct. Here no, and prediction was no. Here yes, yes, no, no. Here it's not used by malware, but the machine guessed that it was, so that's a false positive there. Okay, and then we get down here, we can see the precision, value, recall, accuracy, and F1 are 0.8, similar to what we got over here. And then in terms of our confusion matrix, we predicted that it wasn't infected 83.6% of the time, and when it was, we got it right 76.8%, but we're getting it wrong 16% there and 23% there. Anytime we can actually show the SPL used to be able to create that, so we could store that and open that up, but we can also open up our search on its own, and we could investigate this here. So this is the SPL for actually creating our confusion matrix here. The way to read this is that there are certain scores that we get, and the scores will generate, in this case, a number of those metrics that we saw before, such as precision, recall, accuracy, and F1. Okay, so we can run this on its own if we want, and we can modify it as required. Okay, so now let's go and try another method. If we remember that we got a score of 0.8, we will now try SVM. So with this, we can put in some optional parameters, but we'll just go with the model as it is, just to see if this is a better model for this data set. Okay, so as I said, the model is the data set itself is looking at data collected from from a firewall and identifying if a device is infected by malware or not. So we'll let it run and we'll see how we get on. Okay, so while it's running there we go. Let's see if we've got our model yet. Just run it now. Okay, so the first one we ran was linear regression, and we got a score of 0.8. We're now selecting SVM, and we'll see what score that we get here. Okay, whenever we see a draft here, it means that we can now save this and to be able to recall it at a later time. Okay, so it's getting a few wrong here, but now you see the metrics are 0.96, which is much better, and we've dropped to below 1% for actual and predicted no, and we're down to 7.8% when it predicted no, but it actually was infected. So a success rate of the true positives of 99.2 and for 92.2 for a true negative. Okay, so we can see we have an even better model. But let's try one of the best ones that we have, and that's the random forest classifier. Again, we can use various options to be able to better fit our model, but we'll just go for the defaults just now. And we'll see how we get on with this one. So when I run this last time, I got 0.99. So it's almost perfect in terms of predicting the model. And we'll see it's very quick to run too compared to the other ones. and now we're getting 0.96. We'll just run that model again just to see if we get the right one. And it's just running, so we'll see what results that we get for our random forest method, random forest classifier. Okay, so it's now fitting the model. Random forest uses a number of different models to be able to define our classification. So remember, we're dealing with classifications here, and this is a numeric output. Now there's only one here just in our little sample here. It's getting all those ones right. There's one wrong there. There's another one, and these ones are all correct here. So now we get an accuracy of 0.98, and we're down to just about 1.5 up to 2% there. So we're getting a very strong result here in terms of the results that we're actually receiving. So in terms of that analysis, we can see that the random forest one predicted much better than SVM, which was better than logistic regression. Okay, so let's look at another data set. In this case, we're going to look at race day. So in this experiment, what we'll do is that we'll try to predict a categorical field again. We'll create an experiment, we'll call it cars in this case, and then we'll input a track day. So track day actually is measurements taken from vehicles at a racetrack, and it's measuring speed and speed engine and engine coolant and battery and G-force and so on. Okay, so we'll open up our data set, and this time what we'll do is we'll use logistic regression again, and we'll predict battery voltage from our data set, and then we'll actually select from we'll predict vehicle type. Vehicle type is a category, so we're going to try to predict the vehicle from each of these parameters. Okay, logistic regression, we're going to pick the category of vehicle type, which might be a 2011 Ford Mustang GT500, and this is a category. So what we want to do is to be able to take the vehicle type and then predict what vehicle we think it is, and we'll see how we get on. Okay, so let's open up this data. Let's open up this data set. Okay, so if I go to my experiments, and I'm going to predict categories. This is my example here. Okay, so I just want to use the data set, which is input lookup track day.csv. Okay, so we can have a quick look to see what that data set looks like. If we just press the search just now, then it's there. Okay, so here are the vehicle types in there, and that's what we're going to try to predict for our categories. So we'll use logistic regression. Again, we've got the same algorithms that we can select for this, but this time we'll use vehicle type, and it populates it for us with all the rest of the parameters. We can select them all if we want, and 70-30 is fine, and then we'll go and try to fit that model. Okay, so remember we're predicting a category and not a numeric value. So these are the methods: logistic regression, SVM, and the random forest regressor are the methods, some of the methods that we can use to be able to predict a category. Okay, all the other ones are numeric values, only vehicle type is a category in this case. Okay, so there we go. Let's see what results that we get. And we can see here it was incorrect for this guess. Here, we'll try another one. It's fairly accurate. We're getting it right most of the time. Sometimes the vehicles are incorrect. But we're getting a value of 0.97, which is quite good. And this is now shown as our confusion matrix, where this is what we've predicted. This is the actual, and then this is predicted. So for the BMW M3, it got it right 99.8% of the time. And we can see that the times it got it wrong. Thought it was an Audi, and there's one time it thought it was a Porsche. Okay, this Mustang one looks a bit strange too. That's fine, but sometimes it was getting it mixed up with the Porsche there. Okay, so we can then go ahead and we can try another model. So we'll try our SVM this time. And the last time we improved the category prediction. We got 0.97 for the logistic regression method. Let's see what we get in terms of SVM. Still fitting the model. So it looks like this one takes more time to fit than the logistic regression method, but hopefully we'll get quite a good accuracy on this one. There's 50,000 results in there, so there's a lot of data to be able to go through. So that's why it's taken a little bit longer to run the model. And there we go. Let's try again. Okay, so it's just running the model, and we'll just let it run until it makes its prediction. As I said, 50,000 records, so there's a lot of data to go through. It's taken 70% of that data and then using that to train on. And hopefully we'll get a result coming through. There we go, there's a draft that we can actually now save that. Okay, and then in this case we're getting... It's not looking great for this model. Perhaps the logistic regression method was actually better in this case. And we can see the recall is fallen to 0.64. We're getting an F1 of 0.67, so it's not great, and it's certainly a lot worse than it was before. It's getting quite a lot wrong here. It only got this one correct 65% of the time. So we can see here that this method is weaker than the other one. So we'll just try this one, just as to see how we get on with this last one. So as I said, you save your experiment up here, and that allows you to be able to recall it back again. Okay, we'll come back on to the pre-processing steps a little bit later. but we can pre-process our data to make it fit, to make the data fit better to the model. So we'll just let this one run and just see how we get on with this one. Okay, it's looking better already, and we're getting a really good accuracy here. There's 100%, and there we go. So we can see that the random forest classifier has got actually every single one correct, and it's managed to find a much better model than both SVM and the logistic regression. Okay, so there's the actual and there's the predicted, and you see that it's got it right all of these times. And I think there's just one or two little errors here, but most of these vehicles are predicted correctly. Porsche one, not quite there, but just a 0.4 off, and this is 0.4 here. So there's just a little bit of variation in the model. Okay, so we went for logistic regression, and then we went for the random forest method, and that was definitely the best one there. So now we'll look at predicting numeric fields. The last one we predicted categories, and this one will predict for a numerical value. Okay, so what we'll do is we'll use this dataset here. So this is a dataset from the US, from US states. This is the region state here. Population, the motor vehicle death rate, infant mortality rate, homicide, and so on. Okay, employment, suicide death rate, stroke death rate, smoking death rates, and so on. And hopefully we should be able to train on this to make some predictions based on the data that we have. Okay, so we'll select a numeric field. We'll create a new numeric prediction model, and then we'll go ahead. Okay, so in this case, what we'll do is we'll apply linear. In the first case, we'll apply linear regression, and then we're going to train on a cancer death rate and see if we can actually predict that. In this case, we're getting the residual, and the residual is the difference between the predicted value and the actual value. When we want to look at the quality of this, we will take each of the residual values and then we square and then find some sort of average of that. Okay, so we'll go ahead and we'll see how we get on with this one. Okay, so we have 51 results for the states in the US. So here we are. Average income, CO2 emissions, cancer death rate. This is the one we're going to try to predict. Drug poisoning death rate, and so on, population. So we'll try initially linear regression, and we'll take cancer death rate there, and then we'll take the rest of the parameters, 70-30, and then we'll fit that model to see if we can predict that. And obviously there are certain things that will relate to this cancer death rate, such as smoking. So it just takes a little minute to create our model. There we go. Okay, so this time it isn't a category, but what we get is there's our plot here. and then we get an R-squared statistic that shows us how well we've measured, and we want to get as close to 1 as possible. And then we also get the root mean squared error. That's the square root of all the square root sum of all of the errors in our predicted values against the real values. So in this case, 11.7 is that value, and then we could look at other models and determine if that's a good model or not. So in this case, here we go. So this is the actual value that we have for this, and then this is the predicted, and we end up with this residual. So that's been a bad guess, that's a good one, that's not a bad one, not bad, and then that's a poor one there. Okay, so all these residuals are then squared and added, and then we take the square root. And we can see here, this is the prediction here. So this was well out for this one, and this one was well out, but most of them are coming in and are fairly close to our predicted values, but we also have these outliers here. Then in terms of the errors, we can see that most of the errors are fairly low, but we're getting some that are up 32, 25, 16 and so on. So these are very poor estimates, and these are pretty good. We're mostly positive errors and just a few negative ones in there. Okay, and then what we get is a coefficient value here. So in this case, we can actually determine the most correlated factors related to our training. So for cancer death rate, we can see that homicide and stroke death rate and unemployment are highly or strongly correlated, and then the ones that are less are to do with the motor vehicle death rate, infant death rate, and so on. Okay, so we'll try one more model, and we'll go for a random forest one and see if we can improve on the 11 value that we got for our root mean square. Okay, it just takes a little minute to add the data. There we go. Okay, so if we look at the residuals, yeah, there are a lot of negative ones in there. So the values look a bit high here. You can see that here. So we've kind of over predicted there for each of the states. And there's a trend there. And the residuals, so we can see here, yeah, we're a lot more negatives in there, but the outliers aren't quite as big, although the one is pretty bad here. They're mainly around the 0 and mainly negative values here. And the thing to notice is that we've improved our model. We've brought the R-squared value up to 0.54, and we've reduced the root mean squared error. In terms of the importance, it's coming up with heart disease death rate again as a strong correlator, and then these ones are less in terms of correlation, and we can search through these things here. Okay, so that means that we've improved that. Okay, so we would typically save our project, our experiment, and be able to run other experiments on it. Okay, so in this case we do our analysis, and then when we try our models, we should be able to see, hopefully, that that the methods improve. In this case, I've used lasso, and we're down to 7.7 for an error there. The other area that we look at is called clustering or grouping together, and that's used fairly extensively in defining different categories for our data. Then if we have a differentiation between each cluster, we can simplify the model that we have. Okay, so we'll go with our cluster numeric events here, and we're going to look at a data set called app usage. Okay, so in this one, what we've got is this is the usage of online services within IT services within an organization. So this is the CRM system and the number of accesses per day. This is for the clouds drive, ERP expenses, HR2, IT ops, and so on. Okay, and then in this case, we'll select our clustering method, k-means. We'll look at the thing that we're going to cluster for, and then we'll define the number of clusters that we're going to use. So in this case, it's just 2 clusters, and then we're going to analyze each of these data sets against each other to be able to understand how we can cluster our data. Okay, so here we go. This is app usage. So there we go. That's the data set there each day. And this is the amount of accesses there was for each day. And we'll see if we can create clusters for these. So we'll use k-means first, and then we'll use all of the parameters, and we'll see if we can cluster into 2 sets, and that's the value of k. Underneath, Splunk is using sklearn with Python. So underneath here, the search language gets translated into Python code. So there we are. So what we can see here is here's the clustering of the CRM, a cluster here of activity, and then against the cloud drive we have another one here. Okay, so in this way we can actually analyze for different clusterings of things. If we found a data point up here or down here, this might look strange because it doesn't fit into one cluster or another. If we need to, we can increase the number of clusters to 3, and then we can reduce down the analysis now to focusing on different clustering. And in this way we can actually analyze and find where the clusters are, and then for our data input we can look to be able to predict into those clusters. Okay, so now we have 3 clusters in there. You can see this one is quite a strong between the cloud drive and the HR system. There is definitely three defined clusters in here of usage again. Over here, the strong clustering around a low usage of ERP and a low usage of HR1, a high usage of ERP and a low usage of HR1, and here is a high usage of ERP and a high usage of HR1. So in this case, we could possibly classify different types of users because of the types of systems that they actually use, and then if they move away from their normal behavior, we could identify that too. Okay, so clustering is used quite often to be able to define where things are normally placed. We can then try different methods such as Birch and DB scan and spectral clustering to be able to analyze our data set. An important area within cybersecurity is the usages of anomalies or outliers. And with this, we need to understand when what looks like normal and when we vary from normal. And the more we vary away from normal, the more of a risk that we could be seeing. So in this case, we'll have a look at phone records, and then for each of these times, there is a number of incoming and outgoing calls, either voice or SMS and so on. And we hope to be able to identify within our time series whenever we have an anomaly, either too many calls, incoming or outgoing, or not enough. Okay, so what we'll do is we'll filter for outgoing calls and see if we can detect our outliers. Okay, so there's the phone usage here. We're converting it into a timestamp. Here, and we're only analyzing voice, and we're going to count by direction. Okay, so there's the data set that we have here. So we just run that. Okay, so here is our calls, and what we do is we span for 12 hours. So we take all of our time-stamped data, and then we'll band within 12-hour intervals. So if you want to see the data as it is, we'll find different times of the day here. It's quite difficult to analyze. So what we're doing is that we're bringing together them in bands of 12 hours. So then we're going to analyze the, just let me check. We're going to analyze the analyze, and what we want is the duration. So we'll go for a duration, and we want to analyze in terms of finding the outliers in terms of the time taken for the calls. Okay, and so these are the outliers, and we can see these are quite large values, and they are there's 13 of those, and these are all the normal values. So you see these are quite low, but our model has found these high outliers for the duration. Okay, and we can train on all of our data sets there. So we can actually select for direction, duration, and type, and then we'll try and find an anomaly which is outside the limits for duration, direction, and type. And we can see these are the ones here that are being identified as our outliers. And we can also look at numeric outliers. So that was a category one. So for outliers, we can detect numerical values. So in this case, we're detecting numerical outliers, and we're going to look at server response. So in this case, we have timestamps and whether the server is up, and the round trip time, the maximum time, minimum, and so on. Okay, so in this case, we're going to analyze for response time. We're going to use the standard deviation method, which will measure the standard deviation in the data, and then we'll take a number of standard deviations away from the norm, and then that will be defined as an outlier. So anything in this band here is okay, and anything outside is an outlier. Okay, so we multiply the standard deviation in this case by 2, so we take 2 standard deviations away, and then standard deviation and 2, and we should be able to see, in this case, there are 33 outliers for the response time on the server, and in this case, the server is acting in a strange way. So we just run that model. Okay, so this is the host performance, and we'll take 1,000 records for that. We're using standard deviation, and so let's take 3 standard deviations from the norm and see if we can detect when it went outside our 3 standard deviations. Okay, so there we go. So we can see there were 14 outliers. This one there, and these ones here. These ones are just popping up here. Probably if we change that to 4 standard deviations, then that will bring in those ones in there. And so it does, and we only get 6 now. So in this way, we could actually determine the running standard deviation for our data within a certain window, and then whenever our responses go out with the number of standard deviations, we could see that as an anomaly, and we might think there's something wrong with the server. And the good thing is that Splunk is showing us when these outliers happened. So 2 happened, and 3 happened on the 19th of February, and then there was another one's few in there. And then we can look at the data distribution for those standard deviations. Let me see, this one here was the biggest outlier, and then that one there, and so on. And in terms of this, this is just documenting the values and what the upper and lower bound was from there. Okay, so this is a very useful tool and for cybersecurity, because we will normally look at normality. If it's a normal distribution, we will then look at the standard deviation and how far it moves away from that. Okay, so there's the outliers there, and that's the threshold. Okay, so if we want, we can look at the SPL at any time of the code that we've actually produced, and this is the SPL here, which actually produces this code here. Another thing that we'll often do within cybersecurity is to be able to forecast values. If we can forecast, we can make sure the resources are there, and also if something is forecasted to be at a certain rate, if it doesn't go into a certain range, then we know that something might be going wrong. Okay, so we're going to select a forecast time series, and in this case it's internet traffic. And so what we get is a variation over time. This is 5-minute intervals, and we get the total amount of traffic that is on the network. What we want to do is to be able to use this to be able to predict what the traffic is like on a certain day or on a certain time, because obviously this will vary through, be it its peak, probably about 9 o'clock when people start work, and then probably it will tail off in the evening, and then at the weekends. Okay, so we're going to use 2 filters here, Kalman filter and Arima, and then we're going to try to predict from there. So there are various options that we can apply, and these are related to seasonal activity, whether we take into account different variations in the season. It might be a long-term trend, or different times of the year we'll see different variations. So let's see if we can get our data. Okay, so we'll go to an experiment. And we're going to forecast time series. And we want internet traffic. Okay, so we'll go for the Kalman filter. And there's only one field, which is bits transferred. And we'll just select this one. This tends to be the best. But we'll go for LL first and see how we get on for forecasting. Okay, so what we should see in this case is a variation Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, Monday, Tuesday, Wednesday, and so on. And then it makes a forecast here. And you can see it's not done that very well because we're using a very poor model. So what we can do is then look at seasonal, because seasonal will be able to make some sense of these changes. In fact, we'll go for this LLP5 model, which should be the best, hopefully. And then there we are there. So this is the prediction here, and this is the confidence around those values. What we can do is we can hold back a number of them to be able to see if we can forecast them. So we'll take it 10 steps back and then try to predict inside the period. So we'll just hold back for 50. And then we'll see how well our forecast has gone. Okay, so this is holding back 50 of the samples, making a prediction on them, and then seeing how well the prediction goes. And you can see there it's pretty good in terms of our predictions there. We're matching it pretty well. And then this is Saturday, Sunday, Monday, Tuesday, and so on. Okay, so in this way we can actually predict, and again we get this R squared statistic. It's pretty good there, and then this root mean square error, and also we'll see forecasting outliers in there too. Okay, so we'll try the other model just to see if it's better. If we remember what we got here, which was 0.985, we'll try for the other one. And we can try different parameters there. We'll just see how we get on with this one. Here. Okay, there we go. Okay, so there's our prediction here for our values, and we can see that we can hold back the values again with this one. Okay, so let's look at an example of forecasting with Bluetooth. So in this case, what we have is a number of Bluetooth devices in an area, and these are the Bluetooth MAC addresses that we see, and the probe here, and the timestamp. And what we'll do is we'll band them together into 3-hour intervals from these timestamps, and then we'll count the number of distinct addresses that we see in there. So we can get Splunk to take this and then produce a much cleaner data set here. Then what we'll do is that we'll apply our filter. So this is what we see here, and then we'll do some estimation about the number of Bluetooth devices that we see. In this case, I think this is the Kalman filter, and then this is the other one. Okay, so we'll just run this one here. So this is taking the span of 3 hours, and then DC is distinct values. So we're taking the address field in our Bluetooth data set. So if we just took that out, I'll let you see what the data set looks like. Okay, we have a field called address, and we put this back in, and we take address field, and DC is the distinct the number of distinct values within inside the span of 3 hours. So we'll run this, and we'll use this model here, and we'll try to forecast that. Okay, addresses. And too few data points. Address to forecast. That's address. There. Okay, sorry, I should have refreshed this data here, and so we'll just get that one again, distinct addresses, and we'll forecast. Okay, so this is in bands of 3 hours, and there we go there. Okay, and this is our prediction here. Again, we can hold back our values, but what we'll do is we'll just apply the other one to it, and we'll make a prediction on that one and see how we get on. Okay, so this is our values here. Okay, so we're going to now look at predicting logins for forecasting. So in this case, this is the number of logins that we see on our system per hour, and then we'll see if we can actually do some prediction on those logins. Okay, so we're going to forecast for logins here. Okay, so there's the logins per day, and we can see there is our Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, and so on. Okay, so again, we can look at our success rates in terms of the R squared and the root mean squared. Okay, one method that we often use is to be able to pre-process our data to be able to bring the values down into a certain range. So for this, we take our normal values, and then we'll reduce them down into a range which is constant across all of our data set. So here we go. Here, when we run our standard scaler as a pre-processing step, we can see the values here are now scaled down into a certain region. So let's give that a try. So let me remove that step. Okay, so we're going to apply a standard scaler, and we're going to scale all of our values here. and then we're running a predictor, hopefully. And then when we view our data, we should find that it's been scaled down. We can then use these fields to be able to train on, and then not one, if we're using a numerical predictor, not one value can override or become more important than any other one just because of the sizes of the values. Okay, so we'll just apply this now. And now we've got some new values here. So these are now our training values. We can see it's now SS, standard scalar. And we're clustering for 6 here. And we'll see how we get on now. Big data set. Okay, so we can now see that the values are all scaled. So there you go. So they've been scaled down between minus 2.5 and plus 2.5. So they're all within smaller regions than they were before. And this allows us to more easily train our data set. Okay, so that's what we get there. So we can add other pre-processing steps, and for this we can use a PCA. So PCA is principal component analysis, and it allows us to be able to reduce the number of fields that we have down. So we could create 3 fields for PCA, 1, 2, 3. And with these 3, it will make it easier for us to train our model rather than having all of these options of these fields here. So if we go back here, what we'll do is then we'll now add a step. And we're going to use PCA here. And then we'll select the values that we want to reduce down to PCA values. So we'll take all of these. And then we'll reduce it down to 3. So we're taking 7 fields and we'll reduce it down to 3 different fields. PC1, PC2 and PC3 will be our 3 values that we end up with, and then we can apply our clustering again on PC1, PC2 and PC3. So it just takes a little minute to be able to do that. But when we do that, we end up with these values here. And then we'll then use them to be able to train our machine learning model. Just takes a little minute to run it. There we go. Okay, so we can do PC1, PC2 and PC3 now. So rather than having the 7 to train against, we now only have 3. So we'll do our clustering again and see how that works. So in this case we can reduce the complexity down, and we can merge our fields into just a few of these PCA fields, and then apply our machine learning model into that. Okay, so these are our pre-processing steps that we see here. We can remove them one at a time if we want, but these are applied before our our machine learning model. Okay, so just wait for that one to finish. We've got 6 clusters to look for, but now what we'll see is the analysis of PC1, PC2, PC3. Okay, and this really simplifies our model. Okay, so that's it there. We can take our scalar, we can then apply PCA, reduces it down, and then we can apply our machine learning model. Okay, so that's been an introduction to Splunk and machine learning.